Welcome to the History AI podcast, where the past comes alive with facts, anecdotes, and a dash of humor. Here are your hosts, Chuck and Marco.
Hey everyone, I'm Chuck.
And I'm Marco. Welcome to the History AI podcast, where we use the latest AI architecture to sift the archives, compare sources, and bring you crisp, evergreen stories from the past.
Today, an energy tale so wild it sounds made up, except it isn't. Long before human engineers stacked graphite blocks in a squash court at the University of Chicago, the Earth itself ran a series of nuclear reactors. Naturally, no control room, no lab coats, just rock, water, and physics.
We're diving into the history of natural nuclear fission, how scientists predicted it, where it actually happened, and why it still matters for everything from nuclear waste storage to the constants of physics.
Buckle up. And yes, this one's delightfully evergreen. The geology isn't changing anytime soon.
Quick refresher. Nuclear fission happens when a heavy nucleus, most famously uranium-235, absorbs a neutron and splits into two lighter fragments, spitting out energy, more neutrons, and a burst of gamma rays. Those freshly born neutrons can hit other U-235 nuclei and repeat the trick. If, on average, each fission leads to more than one new fission, the process sustains itself. Reactor folks call that balance K-effective. When K is more than 1, you're critical, and the chain keeps going.
That more than one depends on three levers. First, fuel quality. You need enough fissile atoms per cubic centimeter. Second, neutron behavior. You want lots of neutrons at the right speeds. Third, geometry. The shape and size of the deposit must keep neutrons from leaking away before they do useful work.
Enter neutron moderation. Freshly emitted neutrons are fast, zipping around with energies in the MeV range. U-235, however, is far easier to fission with slow, thermal neutrons. Water is perfect here. Its hydrogen atoms are about the same mass as a neutron, so when a neutron collides with hydrogen, it loses a big chunk of energy, like a billiard ball hitting an equal mass ball. After a few dozen bounces in water, many neutrons slow down into the thermal sweet spot, where U-235's fission cross-section skyrockets.
Nature's problem is supply. Today, only about 0.7% of natural uranium is U-235. The rest is mostly U-238, which doesn't readily fission with thermal neutrons. But roll the clock back nearly 2 billion years, and U-235's share was several times higher because it decays faster than U-238. In other words, ancient uranium ore was naturally richer. That bump in U-235 turned certain deposits into potential reactors, if other conditions cooperated.
Those conditions are wonderfully geological. You start with uranium mobility. In oxygen-rich groundwater, uranium travels as soluble uranyl ions. When that water meets a reducing environment, think organic material, sulfides, or iron-rich sediments, the uranium drops out of solution and crystallizes as uraninite, UO2. Over time, this process can concentrate uranium into thick, laterally continuous ore lenses.
Now add water pathways. If the ore is fractured or porous enough for groundwater to circulate, you've just invited a natural moderator into the fuel. The water slows neutrons, K-effective rises, and the system inches toward critical. But the deposit's shape and size matter too. A compact, meter to tens of meters scale body loses fewer neutrons to the surrounding rock. A thin, stringy seam might leak neutrons faster than it makes them.
There's also chemistry's veto power. Trace elements can act as neutron poisons. Boron is the classic party crasher. Too much of that, and your chain reaction fizzles. Conversely, a deposit low in poisons and high in uranium, flushed by water and wrapped in rock that reflects, or at least doesn't greedily absorb, neutrons, is exactly what you'd design if you were, well, the Earth.
The last ingredient is feedback. Fission heats the rock and water. Hot water expands and can boil off, which removes the moderator, which drops K below 1 and shuts the reaction down. As the rock cools, water seeps back in, neutrons slow again, and the system restarts. That gives you a natural self-throttling pulse. Heat, pause, cool, resume. No control rods, just physics and plumbing. So the recipe for natural fission is 1. Ancient uranium with a higher U-235 fraction. 2. Geologic concentration of that uranium into a compact ore body. 3. Groundwater to moderate neutrons. 4. Low neutron poisons. And 5. A deposit geometry that keeps neutrons from escaping. Put those together, and you don't just have an odd rock, you have a reactor waiting to happen.
Let's set the table. Nuclear fission is when a heavy atomic nucleus, think uranium-235, splits into smaller nuclei, releasing energy and more neutrons. If those neutrons hit other U-235 atoms, you get a chain reaction.
When humans do it in a reactor, we carefully balance three things: enough fissile material, something to moderate the neutrons so they're more likely to cause fission, and a way to control the reaction, like control rods.
Now imagine the planet doing all of that by itself. No dials, no manual.
The key is chemistry and time. About 2 billion years ago, the natural abundance of uranium-235 was higher than it is today. U-235 decays faster than U-238, so roll the clock back and you've got a richer mix, enough, under the right conditions, to sustain a chain reaction.
Add groundwater seeping through permeable rock as a natural moderator, and a uranium ore deposit that's concentrated enough to reach criticality, and you've got a recipe for a natural reactor.
Enter a crucial human, Paul Kuroda, a nuclear chemist. In 1956, he did the math and argued that natural reactors were not only possible, but likely to have occurred in rich uranium deposits if water was present.
At the time, it sounded like a clever thought experiment. Plenty of scientists nodded, said interesting, and went back to their lab benches.
But Kuroda's paper planted a flag. If anyone ever saw odd fingerprints in uranium isotopes from a mine, like evidence that some U-235 had already been burned, that would be the smoking gun.
Jump to 1972. In France, technicians are routine checking uranium shipments. Nothing glamorous, just quality control with mass spectrometers. Natural uranium has a well-known isotopic makeup, and the star of the show, U-235, hovers around 0.75% by atom. Except this batch looks light. The U-235 fraction is noticeably lower than it should be.
At first, you'd blame the gear. Recalibrate the mass spec, rerun the standards, swap columns, classic lab troubleshooting. But the numbers keep saying the same thing. This uranium has already had some of its U-235 burned away.
Paper trail time. The suspect drums trace back to an ore body near Oklo in southeastern Gabon. French scientists loop in geologists and radiochemists. If this is more than a measurement hiccup, there should be fingerprints. Peculiar isotopes you'd only expect if a chain reaction had once been ticking underground.
They start with the fission confetti. When U-235 splits, it doesn't make random junk. It makes specific isotopes in telltale proportions. So the team looks at elements like neodymium and ruthenium in the ore. Bingo! The neodymium isotope pattern in certain zones leans heavily toward the classic fission yields, and ruthenium shows an overabundance of isotopes you'd expect from fission products, not from ordinary geology.
Then comes the clincher, samarium-149. It's a legendary neutron poison, hungry for neutrons. In a working reactor, SM-149 gets gnawed away by captures, leaving a deficit compared with what you'd see in nature. Oklo's samarium shows exactly that deficit. That means there was once a sustained neutron flux bathing these rocks.
Even the noble gases weigh in. Some xenon isotopes, born as short-lived fission products, got trapped inside uraninite crystals. Those little time capsules carry a xenon barcode that matches reactor operation, not random radioactive decay. From how the gases are distributed, researchers can even infer temperature and on-off cycling, the idea that the reaction pulsed, pausing when hot water boiled off, and resuming as the system cooled.
With the geochemistry screaming, reactor, the field teams map the deposit. Oklo isn't a single magic pocket. It's a cluster of discrete reaction zones, often labeled RZ1, RZ2, and so on. More than a dozen in the main Oklo area, plus related activity at nearby Bangombe. Each zone is a compact body of uraninite-rich ore wrapped in host rocks that allowed groundwater to seep through, perfect for neutron moderation.
Put it all together, and you get a striking picture. Roughly 2 billion years ago, the natural U-235 share was higher than today. Groundwater threaded the ore, slowing neutrons. The geometry of the deposit kept enough neutrons from escaping. The system nudged itself critical, warmed up, boiled off some water, dropped below critical, cooled, refilled, and started again, a natural thermostat. Some studies estimate cycling on the order of hours, repeated over very long spans, adding up to a substantial total energy output.
And the aftermath? Besides the depleted U-235, you've got the ash of fission, rare earth isotopes, traces of bred plutonium, from U-238 capturing neutrons, and daughter products distributed in mineral grains. Critically, a lot of those products stayed remarkably immobile in the rock over geologic time. One reason Oklo remains a touchstone for debates about long-term nuclear waste containment.
So when those French technicians saw the uranium didn't add up, they hadn't found a clerical error. They'd stumbled onto a fossil reactor, preserved in stone, proof that the Earth once ran its own nuclear experiment, quietly, expertly, and for a very long time.
Okay, picture this. You've got a big sleepy block of uranium ore underground. No switches, no control room. How on earth does it decide to, turn on?
Step 1 is the fuel. 2 billion years ago, the uranium mix had more U-235 than today. Think a naturally richer blend. If enough of that U-235 is packed into one spot, you've got the makings of a chain reaction.
Step 2 is the moderator. And this part feels like a plumbing story. Groundwater seeps through tiny cracks in the ore. Those water molecules are basically neutron speed bumps. Fast neutrons slam into hydrogen, slow down, and suddenly they're way better at splitting U-235.
Now step 3, shape and size. If your ore body is chunky and fairly compact, meters to tens of meters across, it keeps more neutrons bouncing around inside instead of leaking away into the surrounding rock. Geometry matters more than you'd think. A skinny seam bleeds neutrons, a stout lens holds them.
There's also the no party crashes rule. Some elements, boron is the classic, are neutron poisons. If the deposit has a lot of those, the chain reaction fizzles. Oklo-style deposits got lucky. High uranium, enough water, not too many poisons.
Put that all together and the system tips into critical, K just over 1, and starts humming. Fission kicks out heat, plus more neutrons, which keep the train rolling.
And here's the elegant part. Automatic shutoff, courtesy of boiling water. As the rock heats up, the groundwater heats and boils. Steam doesn't moderate neutrons like liquid water does, so moderation drops, K falls below 1, and the reaction slows or stops. No human touches a dial. Physics does.
Then the rock cools, water seeps back in, neutrons get slowed again. Click, the reactor turns back on. It's like a geologic kettle. Heat, boil, pause, cool, refill, resume.
Some studies even suggest those pulses happened on the scale of hours. So underground you'd have this rhythmic cycle, on, off, over and over, adding up to a serious energy budget over geologic time.
So the checklist is simple but picky. Richer ancient U-235 concentrated ore, groundwater to moderate, low neutron poisons, and helpful geometry. Hit all 5 and your rock doesn't just sit there, it runs itself.
First lesson, nuclear waste containment. The fission products and transuranic elements, the ash of nuclear burning, stayed largely immobilized in the host rock over more than 1.5 billion years. That's a profound natural experiment for anyone designing deep geologic repositories.
Second, plutonium in nature. Oklo didn't just burn U-235, it also bred Pu-239 from U-238 via neutron capture. That plutonium also stayed put remarkably well in the mineral matrix.
Third, fundamental physics. Oklo is a time capsule for the fine structure constant and nuclear cross-sections. By comparing isotopic ratios from the ancient reactor to what we'd expect today, physicists can put limits on whether the laws of physics have changed over geologic time. So far, the rock whispers. If they changed, it wasn't by much.
Fourth, reactor design insights. The idea of moderation by water and negative feedback via boiling is a familiar safety principle in some modern reactors. Oklo showed that the Earth, through blind tinkering, stumbled into a similar dynamic.
Sometimes people ask, is Oklo the only place? Oklo and nearby Bangombe are the headline acts with clear, sustained chain reaction evidence. Elsewhere, we see spontaneous fission, a natural but rare decay mode in heavy nuclei, and fission fragments made in cosmic ray spallation. But a self-sustaining reactor in the wild. So far, Oklo Bangombe is the gold standard.
It also reframes human history. When Enrico Fermi's team started up Chicago Pile 1 in 1942, it was the first engineered self-sustaining chain reaction. But the planet had already pulled off the trick more than 1 billion years earlier, quietly, underground, without ceremony.
The detective story here is irresistible. A small anomaly in isotope ratios kicks off an investigation. Geologists map ore bodies. Chemists analyze rare isotopes, some with half-lives so long they're still around, others present only through their daughters.
Layer by layer, the story emerges. Ancient rivers concentrate uranium. Tectonics and chemistry lock it into place. Groundwater flows. The reactor ignites. Heat drives water out. The reaction pauses, and the cycle repeats. Over perhaps hundreds of thousands of years, those pulses add up to a substantial amount of energy.
And it leaves behind a geologic scrapbook, depleted U-235, specific distributions of neodymium and ruthenium isotopes, traces of plutonium decay to uranium-235's cousin, U-235's grandchildren, in the rock record. Each page says, yes, a reactor lived here.
Beyond the scientific goldmine, Oklo matters for policy. When debates swirl about whether nuclear waste can be stably isolated for tens of thousands of years, Oklo is a case study that says, look, we've got a natural analog that held on to fission products for over 1 billion.
That doesn't shortcut careful engineering. Rock types differ, water pathways vary, and repository designs must account for those nuances. But as evidence, it's compelling.
Plus, it's just cool. The idea that somewhere beneath a quiet forest in Gabon, the ground once hummed with a nuclear reaction, regulating itself like a kettle. Come on, that's science at its most cinematic.
Here's the big takeaway for me. Oklo isn't a weird exception. It's a reminder that nuclear is woven into the fabric of the world. Start way upstream. Our sun runs on fusion, not fission, pressing hydrogen into helium and throwing off the light that powers photosynthesis, weather, and ultimately us recording this podcast. Every bite of food is solar energy laundered through chlorophyll. So from breakfast onward, you're living on nuclear energy from the sky.
And under our feet, the Earth's slow engine hums because of radioactive decay, uranium, thorium, and potassium shedding heat over billions of years. That radiogenic heat helps drive mantle convection, plate tectonics, volcanoes, the whole restless planet package. In other words, geology has had a nuclear baseline since day one.
Oklo sits right between those stories. Not fusion like the sun, not just background decay, but self-sustaining fission, a naturally assembled reactor. It proves that the conditions for a chain reaction aren't exclusively human inventions. We recognized the pattern and later engineered it, first in Chicago Pile 1, then in power reactors around the world.
And we've used nuclear beyond electricity. Medical isotopes diagnose cancers, sterilize equipment, and zap tumors with targeted radiation. Carbon-14 dating, born from cosmic ray interactions in the upper atmosphere, lets archaeologists timestamp ancient campfires. Even your body ticks with a little potassium-40. There's a faint nuclear whisper inside every living thing.
Of course, there's the shadow side. The same physics that warms a hospital ward also underpins nuclear weapons. That duality is on us, not the atoms. Oklo gives perspective. Nature showed fission can run steadily, locally, and self-limiting when feedbacks are right. Our responsibility is to design systems and policies that honor that restraint.
Which brings us to humility. Oklo is a billion-year materials experiment we didn't pay for. Fission products and even bred plutonium stayed put remarkably well in the rock. That doesn't mean every repository will behave identically, but it's a data point of astonishing timescale, a nudge to let geology be part of the safety case, not an afterthought.
It also reframes natural versus artificial. Humans aren't foreign to nature. We're a natural species that learn to shape flows of energy, fire, steam, electricity, and yes, the nucleus. When we build reactors with passive safety or design fuel cycles that minimize long-lived waste, we're echoing the negative feedbacks nature stumbled on at Oklo. Heat up, lose moderation, calm down.
And zoom all the way out. The elements we're splitting were forged in ancient stars and supernovae. The energy we harvest is a delayed dividend from cosmic events. The sun fuses, the earth decays, Oklo fissions, and humans, sometimes wisely, sometimes not, engineer in that same vocabulary.
So what does natural fission tell us about us? That we're at our best when we're students of the planet, borrowing designs from deep time, measuring twice, cutting once. It says stewardship beats bravado, and evidence beats opinion. The world has been nuclear since the first stars lit. Our task is to make our chapter in that story responsible, boringly safe, and useful.
Well said. We didn't invent nuclear, we just joined the conversation. That's our tour of natural nuclear fission and the ancient reactors of Oklo. If you enjoyed this, please take 10 seconds to leave a 5-star review. It really helps new listeners find the show and keeps these deep dive episodes coming.
Remember, all our episodes are evergreen. so you can queue them up anytime and they'll still make sense next month or next year. Got a topic you want us to tackle? Hit us up on social, Twitter, X, Instagram, Facebook, links in the show notes.
Also, we've got new merchandise. Tees, mugs, stickers, the works. The link's in the show notes. If you grab something, tag us. We love seeing listeners rocking the gear.
The History AI podcast runs on the latest AI architecture for up-to-date, efficient performance. And we're always refining our research workflows so the history stays sharp.
Special thanks to all of you for listening, sharing, and sending in those wonderfully nerdy questions.
I'm Marco.
I'm Chuck. Rate, subscribe, and share with a friend who loves science stories carved in stone. See you next time.
Two billion years before the lights came on, before the wires, before the bombs, the ground was warm, the rain kept falling, atoms pressed together, slowly talking, no hands on dials, no warning signs, just time and pressure, line by line. The stones stay quiet, did the math, split itself and held the rest. No engineers, no master plan, just chance behaving like a hand. The earth learned the trick before we did. Let it burn, then let it rest. A fire asleep inside the grid, breathing in and out its chest. No God above, no switch to pull, just nature proving it was always full of power. We pretend we found, buried deep, humming underground. Water came and slowed the heat like lungs, deciding when to breathe. Turned it off and on again. A perfect pause, a calm restraint. Isotopes wrote their own scars, locked in stone like fossil stars. Nothing leaked, nothing screamed, just patience in geology. If the earth could learn control, why do we rush to lose our soul? The earth learned the trick before we did. Let it burn, then let it rest. A fire asleep inside the grid, breathing in and out its chest. No God above, no switch to pull, just nature proving it was always full of power. We pretend we found, buried deep, humming underground. We split the atom and called it ours. Built our cities, built our scars. Lit the night, burned the day, then wondered why it slipped away. But under Oklo, silent stone, the past still waits perfectly alone. A lesson written in decay, that power doesn't need to rage. It turned itself off when it needed to. It knew when to stop. Do we ever do that too?